name's Logan, and welcome back to the lecture hall. Today we're going to be covering section 2.2, the limit of a function. So I've talked a lot about limits in the last few videos, so I'm sure you're all super excited to learn what a limit is. Well, so let's start off with the definition. The definition of a limit is, suppose f of x is defined when x is near the number a. We write it in the form limit as x approaches a of f of x is equal to L. So, pretty much, as x gets close to a, the function output, we'll say y, gets close to L. And this is the notation for it. So, there's another form of notation that looks like this, but it's not used very often. But if you want to do it on like one line, or if you're trying to type it out, it looks it's a lot easier to type out. So, looks like this: f of x approaches L as x approaches a. So now let's look at it with some numbers. Well, so we have our limit as x approaches 7 of x squared minus 5x plus 4. So we plug in 7, right? 7 squared minus 5 times 7 plus 4, that's 49 minus 35 plus 4. That equals 18. So you just plug in 7, correct? Well, for this one, you can. But you can't always just plug in the numbers. So here, I'll show you an example of where you can't just plug in the numbers. Let's say you had the function limit as x approaches 1, x minus 1 over x squared minus 1. So, if we plugged in 1, we would get 1 minus 1 over 1 minus 1, which is 0 over 0. And that's no good. We don't want that. But if you were to call the definition, it's as x approaches a. So it would be as x approaches 1. So, like we did for the last video, I'm going to make a table, and you have to make it for both sides. So when x is less than 1 and it approaches, and when from the right side, when x is greater than 1, but still approaches 1. So I'm going to make the tables right now. So we have our limit as x approaches 1 of x minus 1 over x squared minus 1 is equal to what? Now we look at our tables. So we look at the left-hand side and the right-hand side. So on the left-hand side, what you do is you just make numbers that are close to 1, and you keep getting closer and closer. So we start off with 0.5. So x equals 0.5, f of x equals 0.667. So, and then x equals 0.9. F of x equals 0.52637. And then x equals 0.99. We're starting to get close to 1. F of x equals 0.502513. Okay. Alright, if you're trying to, I hope you're starting to see a pattern. So then you go 0.999, it's 0.50025. 0.9999, it's 0.50025. And it's starting to get closer and closer to 0.5. At least that's what it looks like, right? Well, if it does, on both sides, then the limit is equal to 0.5. And spoiler alert, it is. So now we go to the right-hand side, it's 1.5 and 0.4. And then 1.1 is 0.476190. Okay, that's starting to get close. And then 1.01, 0.497512. And then 1.001 is 0.499750. And then 1.0001 is equal to 0.49975. Alright, so we can see, since both limits approach the same number from each side, that means that the limit of x, as x approaches 1, of x minus 1 over x squared minus 1 is equal to 0.5. So now let's change the function we have, and let's look at, so this is our f of x, and then now let's have g of x. G of x will be a piecewise function, x minus 1 over x squared minus 1 when x does not equal 1, and then it equals 2 when x equals 1. Right? So then we have our f of x. I'm just going to rewrite it. Alright, so we have our two graphs. So we have our f of x and our g of x. Well, so they look pretty similar, and so the graph is just a decreasing graph from negative infinity to positive infinity, and right here, when x equals 1, there's a hole in the function, because it can't actually equal anything, because then we get that dreaded 0 over 0, but we have a hole at 0.5, right? So with g of x, it's the same thing, and we have a hole at 0.5, but then we have a point at positive 2. Well, so what are the limits of both of these? Well, actually, they're the same exact thing, because it's not when the limit of x equals 1, it's the limit as x approaches 1. And so we can see here, the limit approaches 0.5 on the y-axis, and here, the limit approaches 0.5 on the y-axis. So even though the limit for g of x when x equals, when g of x, when x equals 1 for g of x equals 2, even though that's the case here, they're still approaching the same limit, which is at 0.5. Alright, now onto another function. F of t is equal to the square root of t squared plus 9, outside of the square root minus 3, all over t squared. What is the limit as x approaches 0 of f of t? So, what you should always just do, because just to see if it works, you can always just plug in the limit, just to see if it works. Because remember the first example I showed you, where you just plugged in 7 and you got 18? Well, sometimes that will work. Other times, not so much. You plug in 0 into f of t, and you get 0 over 0. And again, we don't want that. Nothing over 0. If it was 0 over 1, that would be fine, because that equals 0. But we just can't have anything over 0. So, now we go to our handy-dandy table. And the great thing about this function is that your t's are all going to be always positive. So, you can just plug in the positive versions, and that will be equal to the positive or negative, because they're going to be squared, and a negative squared is a positive squared is a positive. So, for this one, you only had to make one table, because they're going to all equal the same thing. You don't have to go from the right hand and the left hand side for these. So, plug in plus or minus 1, that equals 0.16277, bunch of other decimals, and then plus or minus 0.5, you get 0.165525, more decimals. Plug in plus or minus 0.1, you get 0.16620, more decimals. Plug in plus or minus 0.05, 0.1666500, bunch of other decimals, and then you plug in plus or minus 0.01, and you get 0.16666, more decimals. So you can presume that it's getting closer and closer to 0.166 repeating, right? Well, as I'm sure all of you know, just off the top of your head, of course, everybody knows this, that's equal to 1/6. So the limit as t approaches 0, I had x this whole time, it's t. As t approaches 0 of t squared plus 9 all in square root minus 3 over t squared is equal to 1/6. So now we're going on to one-sided limits. And we're going to start off with the definition of a one-sided limit. Alright, so the definition of a one-sided limit, we write the limit as x approaches a minus of f of x equals L, and say the left-hand limit, which I'm going to be abbreviating to LHL, of f of x has, or as x approaches a from the left is equal to L, right? So that is the LHL, the left-hand limit. But now, if we're doing the right-hand limit, we just cross out L, we change that to a plus, change that to right, and it's the same definition, it's just a different side and a different sign. And for right-hand limits, I'm going to say RHL. Alright, so now let's look at a very important and very simple limit where they have different one-sided limits. So, the Heaviside function, and this is named after the electric engineer Alvin Heaviside, and it's described as an electric current that is switched on at time t equals 0. But we don't really care because that's physics, and this is all about math. I'm joking, of course. But, so, now we look at it. H of t is equal to 0 when t is less than 0, and h of t is equal to 1 when t is greater than or equal to 0. So, as the limit, so we see from the graph, as the limit as x approaches 0 minus, it's not negative 0, it's 0 to the minus side, it's the left-hand side of 0, of h of t. Now we look at our graph. So as 0, we're getting closer and closer and closer and closer to 0. So this is equal to 0, right? But now if we're looking at the 0 plus, x approaches 0 from the positive side, h of t is equal to what? Well, so we move along and we see, oh, it approaches 1. So we can see from this function that a function can have two different side limits, but if the side limits are, the one-sided limits are different, then the limit of a function does not actually exist. So now we can use the definition of one-sided limits to ascertain if a function or a limit of a function actually exists. So, to see if a limit exists, the limit of x, as x approaches a of f of x exists, then we have this symbol, if and only if, just remember, if and only if the limit as x approaches a positive of f of x is equal to the limit of x approaching a minus of f of x. So, the limit of a function exists if both sides approach the same place. So, like the function we had before, our f of x is equal to x minus 1 over x squared minus 1, that limit exists because they approach the same place, just like our square root of t squared plus 9, and then outside of the square root minus 3 all over t squared. That exists at 1/6 because both sides approach the same place. So, now, onto infinite limits. We're going to start off with an example and a table. So, we have the function f of x is equal to 1 over x squared. What's the limit? The limit as x approaches 0 of 1 over x squared. Well, we plug it into our table, So we have x of positive or negative 1 equals 1, and then we see x of positive or negative 0.5 equals 0.4, or equals 4, then positive or negative 0.2 equals 25, positive or negative 0.1 equals 100, positive or negative 0.01 is equal to 10,000, and then positive or negative 0.001 is equal to 100,000. And so you can see the trend, it's just exploding upward. And if we were to see a graph, we see, okay, this is the graph of 1 over x squared, and we see both sides are going up, and there is a vertical asymptote, which is going to be very important in about 2 minutes, and we see it going straight up, and we see that the function is just going upwards, and it's never going to hit 0, and it's just going to go up forever. So the limit as x approaches 0 of 1 over x squared is equal to infinity, because it's never gonna touch x equals 0, because that will be 1 over 0, which is not okay, and so it's always gonna get closer and closer and closer up. So it's gonna just diverge to infinity and beyond. Oh, sorry, that was stupid. Alright, now on to the definition of infinite limits. Let f be defined on both sides of a, except possibly on a itself. Then the limit as x approaches a, f of x equals infinity. The values diverge to infinity. The opposite is also true, where the limit as x approaches a of f of x equals negative infinity. This means the values of f of x diverge to negative infinity. So now let's look at another definition. The vertical line A is a vertical asymptote if at least one of these is true. So one of these properties. The limit as x approaches a of f of x equals infinity. The lim of f of x as x approaches a minus equals infinity. The lim of f of x as x approaches positive a equals infinity. And the negatives of those three statements. The limit of f of x as x approaches a equals negative infinity. The limit of f of x as x approaches negative a equals negative infinity. The limit of f of x as x approaches a plus equals negative infinity. And so that is the definitions for an infinite limit. So what would be example? Because I showed one example of a positive a limit that diverged to positive infinity, but let's see one that diverges to negative infinity. So the lim as x approaches 0 of negative 1 over x squared. And so that's just lim of x squared, or 1 over x squared, just negative. So the graph of 1 over x squared looked like this. So that's 1 over x squared. Now the graph of this one just looks like this and diverges to negative infinity. Alright, so now on to a few final notes, and then we're going to be done with the lecture portion. Okay, on to the final note of this lecture. So these are just good to know. So the limit as x approaches 0 plus, ln of x is equal to negative infinity. So we can see here from the graph, as x gets closer to 0, it gets farther and farther down, and it will diverge to negative infinity. So now we have our limit as x approaches tan minus, or limit of tan of x as x equals pi over 2 minus equals infinity, while the limit of x as x approaches pi over 2 plus tan of x is equal to negative infinity. So we can see as it approaches the left side of pi over 2, it'll go up to infinity, while on the other side of the graph, as it approaches pi over 2 from the right, it'll approach negative infinity. So so thanks for watching. That's all for the lecture portion, and we're gonna transition to some of the questions. Okay, now on to the questions. We're going to be doing 2 and 15. So, number 2, explain what it means by the limit as x approaches 3 minus of f of x equals 4, and the limit as x approaches 3 plus f of x equals 7. So, first, what does this mean? Well, it means that the two sides are approaching different limits. So, from the left side of 3, the 3 minus, it approaches 4, and from the right side of 3, or the 3 plus, that equals 7. So, does the limit exist? And from the definition of the existence of a limit, we should know that it does not exist, because the limit exists if and only if both sides of the limit come to the same place. And for this limit, or whatever, these two things, it says the limit approaches 4 for here, for the left side, and it approaches 7. So the limit does not converge to the same place, so it does not exist. Now, on to 15. Sketch the graph. The limit of x to the 0 minus, as x approaches 0 minus, f of x equals negative 1. The limit as x approaches 0 plus f of x equals 2. And f of 0 equals 1. So we know that the limit does not exist, but how do you sketch this graph? Well, so we know, okay, as it approaches from the minus equals negative 1 on the y-axis, and since we don't know anything about this graph, it can just be something sort of like this, and then we have a hole here at x equals 0. And then, so then we have x approaches 0 plus, that equals 2. So then we go up here, do the same thing, all, and we just have our graph. And then we have f of 0 equals 1. So that's like right here. And you draw a dot to signify that's where the point exists. Doesn't exist here or here, it exists at 1, and then once it's close to 0, then depending on which side it either goes up or goes down. So those are the questions for today. My name was Logan. Thanks for watching. Have a great day.